Welcome everyone! In this video I'm going to show you some news about my metallurgical microscope. So I published already two videos about this microscope. One was just about unpacking it and showing its capabilities, and then the other was about this attachment. Maybe if I rotate it you see it better. This one here, which is a motorized Z-axis. And then, of course, I shared several videos and pictures about different transistors and electrical components, which I recorded with this microscope. And I was discovering that the optical performance or optical quality is not the best. And as you can see on the head of the microscope, we have this trinocular head. We have the two eyepieces, and then there's a third, let's call it now eyepiece, but it's a camera piece. So this third tube can accept a camera tube. And in this video I'm trying to talk about these attachments, which you can already see here, because I went through quite some struggle until I found the perfect combination of tubes and attachments. And there are different experiences out there on the internet. So I was talking to some other makers who have very similar or maybe identical microscope, and they just use the same attachment with the exact same camera that I have, and they produce very good images without any vignetting, which I will show you how it looks like. But I am not able to do that with this simple tube. So I'm going to walk you through this setup and then show you how the different attachments perform, and then I will try to explain why they perform like that. So yeah, I will just try to give you some kind of guidance that if you want to upgrade your similar or even identical microscope, then what kind of issues you can face and how you can resolve it. So I moved the camera a bit closer, and we will be focusing on this tube here. So this is actually a movable tube, so I could rotate this, but there are two set screws. One is at my thumb and the other is at my index finger. And if I loosen them, then I can rotate this tube, and I can change the distance between the sensor of the camera and then the lens, or actually the object that I'm looking at. And then this tube has a certain inner and outer diameter that I can measure. So if I take a measurement on the outer diameter, then that is like 25.12 millimeters. And then I can measure the inner diameter, which is actually more important. And that is about 22.9 millimeters. So then what we typically do is the following. We want to attach something to this tube, which will then hold the camera. So as I showed earlier, I have this piece. So this side will go into the tube, and then this side here has a simple camera mount which goes on my Sony Alpha 6000, a very simple mirrorless camera. So then how it works is that it just simply slides in here, and then on the back sits the camera, which I will show you later. But then with this setup I have the problem that I have strong vignetting around the corners. So basically I just see a circle out of the full image. And the reason for that is because how the image is cropped on the sensor. So due to the distance between the optics and the sensor, which is sitting on top of this adapter, the image is not stretched enough. And I will show you what I mean by this. I just don't know the perfect definitions for that, so my explanation is not the nicest, but demonstration will be nice. So due to that, the focused image on the sensor will not fill up the sensor, basically. So then I did some research on the internet and found another adapter, which is this guy here. And here we have the same tube as we have here. So it's simply a T2 thread on this side and then the Sony E connector here. And then this side is an optical adapter. So what we have here is that we have this ring that I can rotate, and that is actually just an aperture. I will try to demonstrate it. You can see the aperture opening and closing. And then here you see the optical element, of course. This also slides into the tube, something like this. And then we would expect that since it has optical elements, the reason for the optical elements is to kind of stretch the image, so then it is projected on the sensor in a way that there are no vignetting, because the image is kind of magnified or cropped. So it fills the whole sensor. For example, if you have a Nikon DSLR and you want to use it with an M42 lens, then you will need an optical adapter, because the flange focal distance of the Nikon DSLR is too large. Now I'm talking about the APS-C. I don't know about the full frame, but for the APS-C it is too large. So if you just put on the normal M42 lens, then the image will be basically sharp in front of the sensor, but not on the sensor. So, for example, you cannot achieve infinity focus with an M42 lens on a Nikon DSLR. But then, if you use a certain adapter, which I can actually show you, this guy here, you can see from the lens flare that this has an optical element. So what this optical element does is that on the left side we have the M42 lens, so here, and on the back side, so towards this side, we have the sensor. And then this just stretches the image a little bit, so then the image will reach the sensor properly, and now you can have an infinity focus with your M42 lens on a Nikon DSLR camera. And I was naive enough to believe that this has something similar feature, that it stretches the image and then I can have a focused image. But no, the vignetting is still there, and I have to crop into the image when I edit it in order to have a picture without vignetting. And thanks to the optical element, or maybe I should not say thanks, but due to this optical element, I also have some distortion. So yeah, that sucks. So then I have the third option, which is the working option. So let's see what that is. So I have this adapter here, and once again, this side is the camera side, and this side goes into the tube right here. And then I found this guy. And this is a simple tube which is actually used for, or should be used based on the product description, for telescopes. So if you are looking at the sky and trying to find some stars or planets or stuff, then this should be used when you want to attach a camera or something to your telescope. And then what this can do is that if I loosen these two set screws, then I can change this distance. And I don't know what's the name exactly of this tube distance. Maybe it has some like a term for it. But yeah, if I expand the tube, then of course the distance between certain optical elements will be larger. Or if I shrink it, then lower the distance will be smaller. And then there is a third set screw, this guy here, because in this tube you can put a optical element here, which is some kind of eyepiece or some kind of lens. So yeah, and then on this side we have a T2 female thread, and here we have a male thread, also T2. So actually I can do the following. I take this guy, and then I can separate it. So then female takes the male thread here, and then obviously this goes on. So now I have this very long tube which actually fits here. And thanks to the larger distance here, now of course I change the magnification as well as the crop on the image, I can have a sharp image on my camera, and it is cropped properly, no more vignetting. So that is, I think, really nice. And the only thing I lose, which is not too much, is that the amount of light hitting the camera sensor is a bit decreased, but that's all. I can do a longer exposure or something, so I don't really care about that. But I get a good picture. So then if you want to use this kind of metallurgical microscope or maybe another one, and you have problems with vignetting, then you just need to increase the distance. So now what I'm going to show you is that I assemble all the 3 lenses. So I will just reassemble the short one, and then I will show you under the microscope how different things look like with the different setup, and then you can understand what's the problem with the vignetting and all these things. So let me assemble the camera, and then we will see what I'm talking about. So here is the camera. So I just simply put it in the tube like this, and then now I will switch to the view of this camera, and then I will show you what the camera sees and what's the problem. So now this is the camera's view with a calibration slide, and we are looking at a calibration slide where a division is 0.01 millimeters or 10 micrometers, and this is what the camera sees with this specific optical route or optical path. And now I'm not going to disturb anything with the microscope, so focus and everything stays the same, at least for now. And now I change to another adapter. So you can see the optical element. Actually, the sensor is sitting much higher than previously, but then we have some lenses in between the, let's say, objective lens and the sensor. So we will see how that will behave. So as I said, I did not modify anything with the optics, so you also look at the unfocused image, and it's unfocused of course because now I changed the optical path, which became longer and it has an optical element. So I try to focus this thing. Something like this. So on the left side of the image you can see the vignetting more, but you can also see some chromatic aberration or some kind of fringe, or I don't know how to call that error. But if you look at the image closely, you can see that the wall field is kind of curved. So it's kind of a pillow or barrel distortion. I don't really see it on the small display, the direction of it, but I can see that the lines are not really straight. So that's not necessarily good. So actually this adapter did not improve anything. And the problem is that it's also very expensive, so I kind of threw out quite some money on the window because it doesn't work with my camera. And I tried to increase or decrease the distance by this third tube on the trinocular head, but it did not help, so that was not the solution. So now I'm going to switch to that third option with the adapter, which can be expanded, and we will see how that looks like. So here's the big boy tube. It's quite long, as you can see. So this will go on the camera. And you cannot even see the camera up there because the distance is so large. And actually this is totally retracted, so this inner tube is hitting the surface here, so I cannot make it shorter. But it's not a problem, and you will see it exactly what the camera sees now. So let's switch to the camera. So right now, this is what the camera sees, and I haven't changed the focus. So the focus is still at the same setup as I left it with the lens with the optical element. So I will have to change this now. But you can see that there is some drop in brightness because of course now the light got a bit less than in the previous versions. So that's one of the drawbacks of using these longer extension tubes. This is also a problem when you use an extension tube like for macro photography. So yeah, you drop the amount of light and you lose light if you have this kind of setup, but of course then you increase your magnification. So let's focus. And now kind of the whole field of view is focused. And yeah, we cannot really see any vignetting. The field, since there are no optical elements, is quite flat. So the lines are really nice and straight and parallel as they should be. And we are still looking at the same calibration slide. Nothing changed. I even used some blue tack to hold down the slide so it's not moving anywhere. I did not move the stage. So this is what we see. And yeah, you can see that the field of view is reduced because we kind of magnified the image a bit. So we can think about this as like cropping some percentage of the image out. Like when you put a full frame lens on a APS-C camera, then you also experience a cropping factor, typically around 1.4, 1.6, because of how these lenses project the image. And kind of the same happens in this scenario. Maybe it's not exactly the same, but kind of the same. So yeah, this is what we can see here. Okay, I want to show you some very informative illustration here, and that will be done with this small square and with this mask, which happens to be the same size as this square. So what we have here is a rectangle with these dimensions, 25.1 millimeter times 16.7 millimeter. And actually this rectangle is the same real physical size of the camera's sensor. And that sensor happens to be the area where we project the image with the lens of the microscope. So then here the masked area is also the same. You can see that it overlaps nicely with the square that I drew there. And I will use it as a tool for my demonstration. Instead of trying to resolve some formulas and some definitions and so on, I will give you a physical demonstration, so hopefully you will understand better how this extension tube works and how it makes it possible to avoid vignetting and so on. So I move to the camera and I show you how this thing works. So here is the microscope, and I will use my mask to demonstrate you how the image behaves when it is projected upwards in this direction. And now everything is too shiny for this demonstration, so I will get rid of the lights, and then I will try to use the camera in a smart way so I can show you what happens to the image. So here we have the microscope, and this is the tube, you can see. I set it up in a perfect way that it's shining the light directly in the camera. So let's put the mask over the tube. And this is roughly the alignment. And you can see that towards the edges we see a circle, because actually that's the heavy vignetting. Because the field of view which is projected on this frame is like rather large. But let's take this frame or this mask and move it up. So you can see that now the image is being stretched, and if the camera starts to focus on this object, we can also see the actual image. So now you can see that the field of view decreased, but in exchange for that, we get rid of the vignetting. Of course, now the microscope has to be focused if I want to get a focused image, but through this you can get the concept that if I go down, field of view increases. If I go up, field of view decreases. So we basically crop the image. And that also means that we get rid of the vignetting. So if I move down, you can see that the vignetting returns because we increase the field of view. But let's go up, and I decrease the field of view. So I crop out more of the actual area that we could observe, but no vignetting. And basically this is the reason why I want to use that long adapter tube, because it will basically solve the issue. You can see that. Now this is kind of the distance of the sensor in real life, where I have the short adapter without the optical element, and you can see the vignetting. And then kind of here where I have the sharp image, that's the real size of the, or the real position of the sensor of my camera. So it's cropped out, but no vignetting. So yeah, that's that. And actually this is also all what I wanted to talk about in this video. Like a metallurgical microscope with a trinocular head, and you have a problem with vignetting, then you just simply have to buy a long enough adapter tube like this, and then use it. I will put links to these products on my website, so check the link in the description, so you can find the cheapest or the most suitable parts for you, and hopefully you will be able to use them in your microscope setup. And I want to encourage you to visit my website, because I took some pictures about the different field of views, so you can have some kind of comparison, so you can see on a large screen with the proper high resolution image how the different adapters behave. And then maybe that can also help you to understand how these things work, because I had some problems understanding these, because there aren't really good resources on this specific issue on the internet. There are a lot of questions on different forums, but there are no clear answers. So hopefully this will be kind of a clear answer, because when I was looking for an answer, this was basically what I was looking for. Some visual information and some rambling about different things that happen to the optical setup. So I hope you like this video. I hope you learned something, and see you in the next video.